All right. All right. So welcome everybody to the second day of the NITheCS focus area workshop on decoding the universe. And our first speaker for today will be Suman Das from WITS, telling us about quantum corrections to the density of states of near extremal black holes.
So computing quantum gravity correction is difficult but important. Important because to understand the singularity of the black hole, or maybe to understand what happened during the Big Bang. But these regions are with very high curvature, so it's very difficult to do quantum gravity there. But in nature, there are extremal black holes. And for these extremal black holes, the near horizon region of these extremal black holes develops a ADS2 throat. And due to ADS-CFT correspondence, we know how to do quantum gravity in ADS. What we have to do, you have to write the gravity theory in terms of some one-dimensional quantum field theory in case of ADS2. So in principle, if we have a near extremal black hole with a very long ADS2 throat, we know how to do quantum gravity in this region. Now, there's some estimation like for a black hole of mass 10 times solar mass and charge which is 0.98 times the mass, the curvature scalar is 10 to the power minus 17 odd, and the temperature is 10 to the power minus 11 Kelvin. So the temperature is very, very small. And when you are approaching towards extremality, even closer to the extremality, like if you are approaching Q towards M, at such near extremal region, the temperature would be much more smaller. And in this very small temperature regime, the quantum gravity correction becomes important. It's like any other quantum system. When we have very, very low temperature, the quantum effect becomes important. And as near extremality, we have ADS2 cross S2 region. We can dimensionally reduce over the S2, and we can write the relevant action as like this, where this is the term that is coming from the ordinary gravity things, and this is the Schwarzian part of the action containing the quantum information. Now the good thing is that as it's a Schwarzian, it's a one-dimensional quantum mechanical theory, you can compute the partition function. And if you compute partition function, then you can compute the density of state. And this is the full quantum corrected density of state, where S0 is the Bekenstein-Hawking entropy, M breakdown is some number that is pi over R0 S0. S0 is the Bekenstein-Hawking entropy, R0 is the radius of the outer horizon of the extremal black hole, and this M breakdown is written M gap in this picture. So below this M breakdown or M gap, the semi-classical description of black hole is not valid, and quantum correction becomes important. From this figure, you can see this. This red one is the semi-classical or classical density of state, which is e to the power minus e to the power s, where s is a over 4 g Newton. But this purple curve is the quantum corrected thing. So you can see that when your mass of the black hole is far above the extremality, these two matches, but as you go beyond this M gap, these two things start to differ. Now, if you have matter in your theory, you can also compute the 2-point function, 4-point function, so matter correlator, that also get quantum correction. So, as a result, any physical quantity that involves the density of states in their computation modify it at the very low temperature. So first thing where this density of state appear is maybe this type of formula. This is very familiar in the from our quantum mechanics course. This is the Fermi's golden rule. So you have an initial state, you have some final state, and if you shine some electromagnetic or something, some perturbation, which is encoded in age interaction, this is the emission rate from the initial state to final state, and this is the density of state of the final state. So now, if in your theory, if you have some scalar, let's say, which is minimally coupled to the gravity, then as now you have a ADS2 throat, near the boundary of the throat, this scalar behaves like source time the non-normalizable part plus the 1 point expectation value times the normalizable part, because this is the structure of the ADS2. And as a result, the effective action can be written like this. So this is the Schwarzian part that I showed you previously, and this is the source term, and this is the one. This is the source term, this is the 1 point expectation value term, and this is the interaction Hamiltonian. So in principle, you can compute this emission rate. Now, what else will happen? So it's like you have a quantum mechanical system, which is the Schwarzian one-dimensional quantum system, and you are signing some electromagnetic signal like psi r omega e to the power minus I omega. You can think it's like classical. So you are doing some semi-classical type of quantum mechanics. If you do this, what will happen? The system start to absorb the energy. This is absorption. The system start spontaneously emit energy. This is spontaneous emission, and as you have spontaneous emission, you will the system absorb, this is the absorption, the system stimulated emission, and as you have stimulated emission, we know from Einstein formula that you will have spontaneous emission, and this spontaneous emission is the Hawking radiation. So from this formula, you can compute the Hawking radiation rate. Now, due to quantum correction, this rho EF will change. This EF age interaction EI, this will also change. This will basically the Fourier transform 2-point function. As a result, the rate of Hawking radiation also changes. So this picture, you can see that when your energy is far above the extremality, the Hawking prediction, which is blue curve, is very close to the quantum corrected rate of Hawking radiation. But when your energy is close to the breakdown scale or below, then you can see that the quantum prediction differs significantly from the semi-classical prediction. But the problem is the rate of Hawking radiation is very slow. So what you can do instead, you can throw some scalar wave to the black hole and try to measure the absorption coefficient. What will happen then, what is the good thing here, is if you have a large occupation number of the scalar field to begin with, this formula will get multiplied by this large occupation number. And if you compute the absorption coefficient, the quantum corrected absorption coefficient, you can see that the classically predicted value is area, and this is this 1 sigma over AH. And if you go towards the extremality, you can see the absorption coefficient increases. Now you can think why it is increasing, because generally for ordinary classical black hole, sigma absorption coefficient AH, so it's somehow measuring the number of state available. And in the quantum corrected regime, density of state decreases, so it should decrease. But here what is happening, when you are computing this absorption coefficient, you have to compute the absorption rate, and you have to subtract the stimulated emission rate. So what is happening here, the stimulated emission rate is actually decreasing. And that's why this is increasing with omega. And if you try to describe this from this formula, this rho EF is decreasing, but this 2-point function is actually increasing, because generally the 2-point function decays exponentially, but if you have quantum correction, then this the decay rate of 2-point function, this exponential decay of 2-point function becomes slower, and it becomes power law. So it's increasing, that it is decreasing, and as a result, the whole term is increasing with omega. There are other scenarios which are maybe more. We can compute this and you can measure this in experiment. Like if we have strange metal, let's say if you have some holographic strange metal, then as it's a strongly interacting system, holographically we can model this system as some black hole system, which is Reisner-Nordstrom black hole, and near extremality, this Reisner-Nordstrom black hole has a ADS2 throat near the horizon. And when you try to compute various transport coefficient like DC resistivity or optical conductivity, this relies on the input from this ADS2 region. Now, as we saw, in the very low temperature limit, the density of states, etc., will change. As a result, those transport coefficient will also change. And this picture is showing how the DC resistivity changes as you decrease the temperature. This is the semi-classical predicted DC resistivity, and this is the quantum corrected. So at very low temperature, these two start to differ. So one obvious question is, or maybe direction is to generalize this result for non-relativistic Lipschitz symmetry type of strange metal, which have non-relativistic symmetry instead of relativistic symmetry. But there exists a literature which is called ADS-CMT, ADS condensed matter theory, where what is done is they are trying to describe the strongly correlated condensed matter system in terms of the holographic gravity picture. So as in the condensed matter theory, we are interested in some system with at least U1 symmetry and finite chemical potential. In the bulk, we have a Reisner-Nordstrom black hole. And as we saw that this Reisner-Nordstrom black hole near horizon region becomes quantum corrected, gets quantum correction when your temperature is very small. As a result, if we try to compute some transport coefficient like DC conductivity, optical resistivity, or maybe the eta by S ratio, this another transport coefficient also, which actually in their computation we need the input from the near horizon region, this will also get corrected. And it's interesting to systematically compute this correction to this transpose coefficient, because I mean now we have some good maybe instrumental so that we can decrease the temperature to very small scale, and we can check how this various transport coefficient changes at this very low temperature. So yeah, this is the
What is the relationship between the JT gravity you talked about and ADS-CMT? Is there a connection?
Yeah, so I mean, when you are dealing with any condensed matter type of system, generally, we are interested in some U1 charge, and so the bulk dual is Reisner-Nordstrom black hole. So when your charge is very close to the mass, this becomes extremal black hole. So when you are very close to, when you are in the regime of very small temperature, this becomes near extremal black hole. And we saw that near extremal black holes, the density of states, correlation function, etc., gets quantum corrected. So as a result, if you try to compute this transport coefficient, which gets input from the near horizon region, this will also get corrected. And now people have computed what would be the correction to density of states and 2.4 correlation function. We can in principle compute various transport coefficient and correction to them. What will happen at the very low temperature?
I see. No, people have already computed those things for last 20 years.
Yes, and they are not quantum. So now we know what will happen in the quantum corrected regime at the very low temperature regime. That they have not computed. They have computed only this DC resistivity.
Okay.
So like we do not know what will happen to eta by S ratio. We know it's 4 pi, 1 over 4 pi from the normal computation. Now, when you have very low temperature, we know that to compute eta by S ratio, we need some absorption coefficient for the ADS black brane. Now, the absorption coefficient of the ADS black brane will change at this very low temperature regime. So eta by S ratio may get corrected in that way.
So my understanding from, from the sort of field theory ADS CFT side is that correction is a 200-page calculation. So do you anticipate a similar level of difficulty for this calculation?
No. If you do a holographic calculation, it's not that difficult.
I completely disagree with you. I know that this is a holographic calculation. Steve Gubser says it's a 200-page calculation. It's very hard for Steve Gubser. So I cannot imagine that this would be any easier. Fair warning.
Okay.
Which calculation I'm talking about?
The quantum corrections to eta rest. So
Oh,
the one of our
quantum
root
correction.
lambda corrections.
And who
Wait.
calculated that upsurge?
He didn't. He said that this was one person did it. It was 200 pages long. He thinks somebody should have done it. Somebody should check it. But he wasn't willing to do it himself.
Okay.
So maybe this is an
He
unfair
died.
question. I've been asking this question for 20 years, haven't found a satisfactory answer, but I'll ask you anyway. In the extreme black hole at zero temperature, you have a large entropy. Whereas in the ordinary materials, you're talking about experimentally verifying these things against. You go to zero temperature, the entropy also goes to zero. Why do these things have anything to do with each other?
Well, yeah. If you see this graph, I would say the density of state you are talking about is e to the power a naught over 4g Newton, I think. Which is very large.
A black hole in the bulk, typically it's extremal, has a large entropy. Whereas, you take a condensed matter system in the laboratory, you set it to zero temperature, the entropy also goes to zero typically. So why would you expect in the low temperature regime that these ADS CFT calculations have anything to do with actual physical materials? I'm not saying you can't compute these
No, yeah,
and so on in these materials, that may be interesting in its own right. But this has nothing to do with the physical material, right?
Yes, but I mean, is it true that I do not know if you actually compute in full quantum gravity the entropy, it would be large, finite.
It's it's going to be at least it's going to be large in the sense that it's going to be scaling like n squared stuff. It's not going to be
Oh yeah, 0 or something, order one number. Yeah. That I had not thought about. Yeah.
I thought these materials called strange metals are characterized by this particular fact that they have zero temperature entropy.
sure. I mean, there are systems like spin glasses that do too, but they're not scaling like n squared. They're scaling.
I see.
No, I don't know.
You mentioned about spontaneous and stimulated emission, and you interpreted the spontaneous emission as the Hawking
Okay.
radiation. Is there any interpretation for the other one?
Stimulated emission.
Yes.
Yeah, I mean, like if you are shining some electromagnetic light or on some, let's say, quantum material, it will spontaneously emit, it will absorb, and it will emit also. So if you, let's say, try to compute the absorption coefficient, and if you throw something to the black hole, what would be the absorption coefficient? Then we must have to take into account the stimulated emission rate, because you are computing absorption coefficient, so it's absorbing minus stimulated emission. So it is needed to compute the absorption coefficient.
Yes, mathematically it is needed. My question is there any interpretation? Like, so your theory predicts that there can be stimulated emission?
There is stimulated. I mean, yeah, there is stimulated emission. I'm not understanding.
The question is about, one is Hawking radiation, and what would be the other thing? Is it some stimulated emission from a black hole, or
Yeah,
like a laser?
no,
not laser.
not laser, but
Then what's the point? I mean,
like if you throw something, then something will come out. If you try to describe this in terms of quantum mechanics, like if you have some scalar field, you are throwing some scalar field, and when you are measuring here, so it's not absorbing fully. Something will come out, and this will include the Hawking radiation. I mean, the stimulated emission also, spontaneous emission also.
Thanks.
Okay, I think, I don't see any question from the chat. I think we can thank, no.
No, I can't see it. Okay. Yeah,
Okay, great. So
Yeah, so for second topic, so once again, talking about holography on the levels.
Okay, so I thank the organizers for inviting me to give this talk. So the title of my talk is Holography from the Lattice. It's not moving. Okay, it's moving. Okay, great. There is a delay. Okay, all right. So mostly I will talk about supersymmetric Yang-Mills theory and its various incarnations of supersymmetric Yang-Mills theory and their lattice constructions for some of the supersymmetric Yang-Mills theories. So supersymmetric Yang-Mills theories, they have many interesting features like confinement, spontaneous symmetry breaking, spontaneous chiral symmetry breaking, for example. Then there is strong coupling, weak coupling duality. So n equal to 4 super Yang-Mills, it has a self-dual point, for example. Then some of them are conformal field theories. Then some of them take part in holography, the ADS-CFT correspondence. So many interesting features, they happen at strong coupling. So when coupling is very large, of the order 1 or maybe 10 or 20 like that. So we need a non-perturbative definition of these theories. So these are quantum field theories, QFTs. So now there is a first principles definition of a QFT, which can handle the non-perturbative aspects of the QFTs, which is formulate the theory on a space-time lattice. So we discretize space-time and put the quantum field theory degrees of freedom on these lattice sites and links, and we simulate the theory using certain algorithms and get some physics results, interesting physics results. Okay. So the question is, supersymmetry and lattice, are they compatible? Is it easy to put supersymmetry on a lattice? So naively, if we ask this question, it is impossible because super Poincare algebra, it contains generators of translations, and translations, there can be infinitesimal translations in space-time, but on a lattice, we have discrete translations. So that can break supersymmetry on the lattice. But there are ways, so we can naively put supersymmetry on a lattice. For example, n equal to 1 super Yang-Mills theory in 4 dimensions, pure super Yang-Mills. So it contains a gluon and a gluino. Okay, so we can put that on a lattice, but there are discretization artifacts. We have to take care of them. Then there is another construction which is called exact lattice supersymmetry. So we can preserve a subset of the SUSY algebra exactly on a lattice. So that would give us some control to recover the full supersymmetric theory as we take the continuum limit of this space-time lattice. So examples are the famous theory n equal to 4 superangles in 4 dimensions, which is the 16 supercharge theory. Then n equal to 4 superangles in 3D, which has 8 supercharges. Then n equal to 2, 2 or 4 supercharge theory in 2 dimensions. Then there are various interesting matrix models like the BFSS matrix model, BMN matrix model, IQKT matrix model, all these models. They all have holographic duals. So these are very interesting systems. So this BFSS matrix model is considered to be a non-perturbative definition of M theory. So in that way, it is a very interesting theory. Okay, so here is a result from lattice. So this is for the case of BFSS matrix model, or which is a non-perturbative definition of M theory. So here you can see these continuous curves. These are coming from supergravity calculations. So some people, some string theorists, they are doing this low energy string theory. They are doing perturbative calculations, and they are getting these nice smooth curves, okay, from the gravity side. Now, the question is, if ADS-CFT correspondence is valid, a Yang-Mills theory, supersymmetric, which does not contain gravity, should capture somehow these gravitational effects, okay? So people did, so authors of this paper, they did some hardcore numerical computations on a lattice and got these interesting data points, okay? So these data points are coming from Monte Carlo simulations. So they agree very well, okay, with the gravitational theory. So this is a validation of the holographic correspondence, okay? So which is a very interesting result. Then here is, so there is a prediction. So we are going to another matrix model, which is called the BMN matrix model, which is a supersymmetric deformation of the BFSS matrix model, which does not break any supersymmetry. And apparently this is the only unique deformation possible of the BFSS matrix model. So this prediction was made by these people in 2015. Again, this is a supergravity calculation. This calculation is happening at some perturbation around a black hole, and you get this result. So this is, so there are 2 parameters in the theory. One is the temperature, and the other is the deformation parameter. So you take the dimensionless ratio, and they computed this strong coupling calculation, which is a weak, which is a perturbative calculation in the other side. So it's a weak coupling, strong coupling duality. So then they asked this question. So this figure is coming from this paper. And they asked this question, can people, field theory people reproduce this result, this T over mu critical value at strong coupling? So it is 0.106. So it is separating 2 phases in the theory. One is a confined phase, and the other is a deconfined phase. So the question is, so we asked this question, can we reproduce this result using lattice simulations of this BMN matrix model? And it was a long computation. And finally, we got this result from lattice simulations, okay? So this is our work. It is published 2025, this year. So we spent like maybe 6 years on this. So we had some problems with our lattice action. There were some instabilities, all those things. So these are our lattice, the simulation results, Monte Carlo results. So this is the result coming from next to leading order perturbation theory. So we can do perturbation theory at weak coupling. And this is the prediction from gravity. So our data is almost approaching this number, okay? So again, we encountered some problems here, some instability with inverting the fermion matrix, all those things. So this is a very good result. So we are happy with this. So now moving on. So how do we do this on a lattice, these simulations? So here is the lattice action of this theory with 4 supercharges, okay? Pure Yang-Mills theory with 4 supercharges. You can see it is So there are certain structures hiding in here. Okay, so we are placing this on a hypercubic lattice. So you have to place the degrees of freedom in certain way so that this action is gauge invariant. Okay, it does not break gauge symmetry, and this action is also supersymmetric. Did I miss a slide?
When you say gauge invariance under discrete subgroup.
Exactly, gauge invariant at lattice sites. Yeah. But it is recovered in the full gauge invariance is recovered in the continuum. Okay, so before putting this theory on the lattice, so how do we place this theory on a lattice? So we invoke something called the twisted supersymmetry. So we combine the supersymmetry group. We combine the Lorentz group on a lattice. It is Euclidean spacetime. So it becomes a rotation group. And there is also an internal symmetry group where we can rotate the scalars around. So we combine the two. So we lock in these two rotation groups and we rotate the field together. Okay, so that means whenever there is a space-time rotation, there is also an internal rotation. So that process is called twisting. So we can rewrite the action in this particular way. So action is, so it is given in a Q-exact form. Yes. Oh, 5 more minutes? Oh my gosh. Okay, so we can use this particular approach to put the theory on a lattice. So this is the lattice action. So let's move on to the 4D n=4 superangles, which is a theory that contains 16 supercharges. So here is the action of the theory. So it contains a gauge field for Majorana spinors, 6 scalars, etc. So we can again put this on a lattice using this twisted supersymmetric formalism. So this is the lattice action. So then algorithms, so there is a way of doing things on the lattice. Once a quantum field theory is given to you, you have to be very careful how to put this on a lattice. So there are algorithms to update the fields. Now coming to ADS-CFT again, so let me move on. Okay, so what can we get from lattice simulations for the case of n=4 superangles? So one is something called the Coulomb coefficient, which is its capital C. So this theory is always deconfined at all temperatures. So this is that is where this makes a connection with the quark-gluon plasma. So QGP is always deconfined. So we can see some signature of QGP in this setup. So here we have the Coulomb coefficient. So there are predictions from holography in these papers. They are given. So it should go like square root of lambda, where lambda is a 't Hooft coupling. So here is a preliminary lattice calculation, which is coming from 2019. After that, they haven't looked at this because it's a painful computation. But what we see is the Monte Carlo results are matching with what is predicted, okay, fit to perturbation theory. So the numbers are, closer to that, but these are small gauge groups, U2, U3, U4. So we haven't gone to higher end because it's difficult. So then the next is the Konishi anomaly. We discussed this yesterday. So this is the simplest conformal primary operator of n=4 superangles. And it has an anomalous dimension, which is given by this. So there is a gamma k, a correction, which depends on the 't Hooft coupling, okay, for the Konishi operator. So there are predictions from perturbation theory, and there are predictions from holography. Okay, so we can try to verify this on the lattice. Again, preliminary results for n=4 superangles. So this result is coming from bootstrap calculations with U2, n=2, okay? And this is coming from next to leading order perturbative calculation. And these are Monte Carlo results. So they are kind of, close to the results, but still it's preliminary. One need to go further. Okay, now the next big question, so this will be something I would like to do in the future, which is the free energy density calculation of superangles theory. So the free energy goes like this. So there is an f of lambda, which depends on the 't Hooft coupling. So for a small lambda, we can do a series expansion, okay, like this. The important thing is there is a 1 here. So this is done, so I forgot to put the reference. So at strong coupling, one can do a strong coupling expansion. So again, not the number 3/4, okay? So this is 1 over lambda something, corrections. So now there is a puzzle or a problem which is called the 3x4 problem. So there is a mismatch. On one side we have 1, and on the other side we have 3x4. But we don't know what's happening in between. Okay, so whether it's smooth or continuous. The good thing about lattice computation is we can do simulations at any finite lambda. Okay, and we can see whether it's a smooth connection or something funny is happening. So we did some computation, like how many computational hours we need to get some basic result. So we get something like 6.4 million core hours, which is a large computational time, but it can be done. It's doable.
7 million core.
No. It's on a supercomputer, on a cluster, okay? Not on a laptop. So then more problems I have been thinking about. So let me finish. So when we do a Monte Carlo simulation, what happens is we start from some random configuration of the field. So you can set all the fields to 0, for example, and let it update based on the action of the theory. And eventually it updates and it reaches this, it finds this equilibrium configuration where the action is minimized, okay? And it will fluctuate around there. And you can see these certain patterns, right? So these are called correlations, okay? They are not completely random. So my question is, can we use some machine learning algorithms to sample directly instead of constructing this chain? So we feed in some input, some training data, and from that, can we produce more simulation data? Okay, so that is what I have been thinking about instead of constructing this chain. Again, there are situations where the system is undergoing a phase transition. Okay, so then the Monte Carlo simulation, suppose we start from here, so it would thermalize somewhere here. Suppose we start from here, it would thermalize here. So ideally, there should be only one chain. It should find the same place, okay? But it can be difficult when we are passing through a phase transition. So again, can we use machine learning techniques to find whether there is a phase transition or not at that particular coupling, okay? So that is also something I'm thinking about. Okay, so with that, let me end. Thank you. Yes,
Yeah,
Will.
so that was great, thank you. So I have a collaborator, Alexander Rothkopf, who's a lattice QCD guy.
Yes, I know the name. I don't know him, but I know the name.
Yeah, super nice guy.
Okay.
And we had these ideas about exact symmetry preservation, because when you discretize, as you say, you lose translations, you lose rotations, you lose everything basically. And maybe this is more for a discussion, so maybe just put a place marker here. We have a nice paper where we talked about ways that you might be able to exactly preserve that symmetry, which seems important. I think you mentioned on like slide 2 that when you start to discretize and you start breaking SUSY.
Yes, yeah, that's right, yeah.
So I mean,
Yes.
if there's time, then could you maybe talk a little bit about that breaking of SUSY?
Sure, yeah, briefly, yeah, we can discuss, yeah.
Yeah,
I think now we only have a minute or two, so maybe it's better.
Yeah.
The other question?
Yes, which,
What's the time scale for computing with three-quarters, realistically? 4 hours. What do you-
I would say within 1 year, roughly 1 year time frame. So you have to collect all the data, let the simulations run at different volumes, the hypercube.
Yeah.
And at different lattice sizes, the lattice spacing sizes, and also at different Tooft couplings. So you need to create this ensemble, like a big table, you fill out. So I would say it would take like a year if you try really hard.
Are you doing this right now?
Not right now.
Okay.
It's on the list. I am right now. I am doing other going down the list. So there are some. So I'm trying to grab the fruits that are easy to catch, easy to grab. So the low-hanging fruits. That's what I'm trying to.
This is a very interesting question. So
It is.
If you look at this,
Yeah.
I think there's something deep happening. So it would be good to see
Yeah.
operation of this little lattice and understand what's happening to the states.
Right. Yeah. Yeah. So this is definitely we are going to look at this. It's something.
Which
Yeah.
standard are you doing this for?
I would say moderate n values for now, maybe 6, 7, 8, something like that. But that is good enough. It's 1/8. That is, the corrections are small, right?
8 is comparable to the 3/4 though, right? It's not that different from,
Yeah, if you increase the number of colors, it's even more difficult, right? The size is getting bigger. So let's, so our goal is to start small and, use the resources we have right now. Yeah.
There's a question from the online audience. I'm not sure if you can hear it, but you can go ahead, Bob.
Hi, I'm not sure if you can hear me. Thanks for the presentation. So essentially, my question is with regards to the first result that you showed, that you said the latest simulation took like 6 years to get the results. Just wondering, is it something related to the model or something related
You
to
mean
the computation?
6.4. Oh, yeah, 6. Yes, yeah. Okay,
So painful, you've already forgotten about it.
exactly. Yeah, once you get the result, then the problem is solved. Huh? Yeah, so it depends on the way we discretize the theory on the lattice. What we did was we went with the simplest discretization possible. So that kind of hurt us a little bit. So we didn't know. So we had to fix certain things. So that took some time. Yeah. So in the very beginning, suppose we knew everything, how to proceed with the algorithms, everything, then it would have been much faster. Yeah. Yes. So you learn. Yeah, exactly. So you learn as you go. So that takes, that adds a bit more time.
Okay, I see.
Yeah. Okay. Yeah.
Okay, thanks.
Okay,
Okay,
thanks.
given the time, we can thank Anosh again.
No. Yes, but no. Let's see, one of them's blank.
All right, so for our third talk today, we have Gary Kemp from UJ talking to us about this, have a different title.
Against singularity and the center of symmetric group outputs. I think you exchanged something.
Right, yeah, thank you very much to the organizers. Nice to be here with you all. So yeah, I'll try start by giving some context to the ideas that I've been thinking about. So in the half BPS sector of the sort of the usual n = 4 theory, there's a UN gauge group. There's a nice gravitational dual, ADS 5 times S5, and it has many interesting states like the giant gravitons and the new geometries, stuff like that. It's also known that when the energy of these half BPS states, when it scales like order n, they're dual to these D-brane states, these giant gravitons. When they scale like order n squared, they're dual to these new geometries. And it's nicely explained with that work over there. Sort of those are the so-called LLM geometries. If you wanted to build and construct these operators in the dual field theory, so that's known, it's been done. So for example, Sanjay's work with Antal and friends. So these operators are known. So for example, if we're just working with a single complex matrix of the theory, so what you can do if you want to build an operator having n Z matrices, NZ fields. You can take a product of them. And of course, you have to take a trace to make it gauge invariant. And the actual trace structure is parameterized by a permutation of the symmetric group Sn. And then typically what you do is you can take nice and particular linear combinations of these multi-trace operators to get your gauge invariant states. And these are the sort of the so-called famous Schur polynomials that you take. And these objects here, these are the characters of the permutations in the irreps of Sm. Now, you can alternatively, well, you can express this operator in the following way. You have a projector, a PR, acting on the Z tensor N, and then you can take your trace. And the projector essentially looks like that object over there. There's some nice normalization factor. But the important thing is this projector lives in the center of the so-called symmetric group algebra, the C of Sn. And it's known that the set of the projectors, where R are this capital R, these are the Young diagrams, the irreps of Sn, it's known that they form a basis for the center, right? There's another basis that's known, and that's labeled by the conjugacy classes of the symmetric group. So this object over here, T mu, is a sum of permutations that belong to the particular conjugacy class that's labeled by mu. Now, a small subset of these T's, that's a small subset is of interest. So if you take Tk, for example, where the conjugacy class here, it's a single cycle of length k. So for example, if you take T2, T2 is just the sum of all the 2 cycles. T3, that would be the sum of all the 3 cycles, and so on and so on. So it's known that if you take T2 up to Tn, they generate the center of the algebra, right? They generate the center of the symmetric group algebra, multiplicatively, taking powers, linear combinations, and stuff like that. Now, even more, I guess, interestingly, you don't need all n T operators. So typically, even a subset of them will be enough, that will be sufficient. So for example, T2 up to this integer here, k star of n, where k star of n is less than n, typically that is sufficient to generate the entire algebra. Now, over the course of our work, together with myself and Sanjay Ramgulam, we've acquired some data on this, this integer k star of n. So if, for small values of n, so if your symmetric group is quite small, you only need T2, for example, right, to generate the full algebra. So for those values of n, then as you go higher, then you need T2 and T3, and so on and so on. So, I guess somewhat interestingly, even at n equal to 81, so if you've got Young diagrams of 81 boxes, there's some, the dimension of the center is something really, really large, but you just need T2 up to T6 that will generate the algebra. And one of the sort of the main sort of ideas that, or the sort of, the ideas that's behind the work that we've been thinking about is, can we say something about the asymptotics of this integer? How does this k star of n, how does it really depend on n itself? Now, in the short term, what we're hoping to do before preferably the end of the decade or the century, we are in the process of proving that this set of operators, T2 up to Tk star of n, they actually form a monomial basis for the center. So objects that look like this, so T2 to some power, T3 to some power, and so on and so on, this actually forms a basis for the center. So we're developing an algorithm that is able to construct all of the projectors, for example, of the PR, the PRs in the space. So we're developing this algorithm that constructs the projectors, and specifically this algorithm that we're working on, it tells us exactly what monomials to use. So just to give a bit of a flavor for how this thing is working. So the algorithm specifies exactly which monomials we need to use. So just to get an idea, we start with T2 and then we take powers up to some, let's say N2. Then we have a single power of T3 and then we take powers of T2 up to some point. Then we work in T3 squared and then powers of T2 and so on and so on. Eventually T4 enters the game. Then we take powers of T2 and powers of T3 successively, larger and larger until eventually Tk star of n, that enters the game and so on and so on. So we have objects that look like this and we take linear combinations of it and everything like that. And this is what our algorithm, our algorithm specifies exactly what these ends are that we need to take. So we've got a spanning set composed of these monomials. And we also give a proof that the number of these monomials, as specified by this algorithm that we're working on, is also the dimension of the center itself. So that's also a good thing to have. And a crucial input, so I'm not going to, can always talk about details later, but a crucial input is the character table for Sn. Specifically the characters of these, the T operators, right? So the hat there is the normalized characters. And there's a nice, story about the physics that, if you know the normalized characters, these normalized characters of those T's are related to the Casimir operators of the UN. And through ADS-CFT, these conserved charges or these Casimirs are related to charges of in the dual spacetime. So, there's an observer in the space-time, in the ADS, busy measuring these multiple moments or these conserved charges, and slowly but surely they're building up enough information to actually uniquely identify the state itself, identify the Young diagram. So that's, I guess, what I would say for the immediate future. Maybe a little bit something more long-term. So somewhat recently, Sanjay and also a collaborator of his, formulated the measuring or the detection of these projectors or of these states, the PR, in terms of a quantum computation algorithm. So specifically the quantum phase estimation. So in that work, they drew the quantum circuit and had unitary gates based on those T operators and so on and so on. And so they basically formulated the measuring of these states as a phase estimation algorithm. And he also had some nice complexity estimates, sort of minimal circuit depth that you need to perform this detection task. And interestingly, this integer k star of n was also playing a crucial role in these complexity estimates. So this kind of gave a nice novel way, I guess, of looking at this k star of n. So one perhaps idea that, hopefully not too long from now, is we have what seems to be a state construction algorithm, right? So we're developing this algorithm that actually builds these projectors. So can we formulate this as some kind of quantum state preparation task? We've got these basic building blocks and these T operators, T2 to K star of n. So can we formulate this as some kind of preparation task? And if we can do that, can we say something about complexity? Can we classify the complexity of this particular algorithm or this task? So if you like, we have some kind of target state that we want to build. So can we formulate things like that? And also perhaps this might give another new insight into our integer k star of n. So, and of course, maybe, interestingly, or most interestingly, we can hope to maybe do this for states, when n becomes very large. So you're dealing with these really heavy objects in the dual space-time. But anyway, the hope is to formulate this as a state preparation task. Okay, good. So that's one line of investigation. Another line of investigation. So if we go back to the list of normalized characters, if this list is distinct over all of the EREFs R, then it's known that T2 up to this T over here, that's capable of generating the center. But even more than that, if this list is distinct, you can use this list to distinguish between two different EREFs. You can just, if this list is different from the list for another Young diagram, you can use this list to distinguish R from another Young diagram. But of course, if there are degeneracies, you lose this distinguishability. So I asked the question some time ago, said, what shapes do these Young diagrams, what shapes do R and S typically have to take if they have their normalized characters being degenerate? So I proposed a conjecture that was based on, firstly, this idea of majorization, but my conjecture was based on a generalized notion of majorization. So firstly, majorization is it's a partial ordering on the space of Young diagrams. So, just for example, it's known that if Young diagram S majorizes R, then necessarily the normalized character for T2 of S is greater than that of R. So, it doesn't matter what shapes the R and S are, how big they are or whatever, if the one majorizes the other, T2 is enough to distinguish the one from the other. However, if neither majorizes the other one, then they're incomparable. So what I did is I introduced a number, which I called K-swap RNS, that in a sense measures how incomparable they are. So before this, as to the best of my knowledge, there was just comparable and incomparable according to this majorization scheme. But what seemed to really play a role here is just how incomparable they are. And that integer that I introduced, that's measuring precisely that. So my conjecture looks essentially like this. So here, this K star, this is the minimum number of T operators that you need to just distinguish R from S, right? So that the normalized characters is different. So this is what my conjecture looks like. So for example, if you measure K-swap for R and S to be 2 and you plug that into the right-hand side, you get 4, right? So then according to my conjecture, it's absolutely guaranteed that T2 up to T4 is enough to distinguish R from S. And, this integer here, you can obtain it just by inspection. You take your bare eyeballs and you stare at RNS and you inspect it, and it's quite easy to then obtain what that number is. So it's quite easy to obtain. Now, in that work that I referenced earlier, I believe I proved the conjecture for K-swap equal to 1, right, for quite general RNS. I also proved it for K-swap equal to 2, but for a minimum number of 1-box moves. So if you start from R, for example, what's the minimum number of boxes you need to move to go from R to S, such that K-swap is 2. So I managed to do that. And one idea that I'm working on now, it seems plausible that I can generalize this to higher swaps, right? But also for the minimum number of 1-box moves to produce the necessary level of incomparability. And the key thing that I'm using here is that, well, it's kind of known that you can express these normalized characters in terms of symmetric polynomials, in terms of the row lengths. And before I was using power sums, I was expressing the normalized characters in terms of power sums. But of course, there's nice relationships between, the various symmetric polynomials. So if I phrase things in terms of the elementary symmetric polynomials, they have some nice properties that you can leverage. And I seem to be able to generalize and extend this conjecture. So the overall ideas that I'm thinking about, so I'm exploring the idea of this incomparability between partitions as a way of distinguishing them. If you restrict yourself to Young diagrams of 2 rows, I think it's known that you just need T2, right? So the quadratic Casimir is enough to distinguish. If you restrict yourself to Young diagrams of 3 rows, then you need the quadratic Casimir, so T2, and you need the next highest Casimir. So for me, that's T2 and T3, and so on and so on. But yeah, I'm kind of interested in exploring the idea of this new measure as also playing a key role in being able to distinguish the irreps. Also, how relevant is this generalized dominance ordering, this incomparability measure? How relevant is that for other things? Majorization and incomparable diagrams also plays a role in quantum computing, or quantum information rather. So, maybe this has a part to play over there. I haven't thought too concretely about that, but it's nice to maybe think about that. I'm also interested in exploring the 2-matrix problem. So the generalization of those Schur polynomials are so-called restricted Schur polynomials. And these objects over here are the restricted characters. and also in the earlier work of Sanjay, he wrote down Casimir-like operators that was actually capable of distinguishing between all of these labels. In particular, these labels alpha and beta over there. And there's lots of nice, interesting physics of restricted Schur polynomials, and that's been discussed by people like Robert and also recently Yaku as well. So that's another interesting avenue. Of course, the state preparation for P of R, as I've already explained. And then, perhaps being guilty of sucking ideas out of my thumb, but, is there some nice, interesting polynomial ring structure for these T's? Can I phrase this, can I think about these T's in terms of a nice polynomial ring? Are there Grobner bases for these kinds of objects? Things like that. So that's also sort of on the horizon to explore. Some of them I've thought a little bit more concretely than others, but these sort of an overall set of ideas that I've been thinking about recently. So yeah, and I think that's it. Thank you for your attention.
So the things you're doing, you have the small number of boxes typically, right?
That's right.
What are the how do you extrapolate this large N? So this is sort of where the black hole interest lies.
Yeah. That's right. So yeah, so that's indeed a very hard problem. So Sanjay does have some estimates. So I think he came up that there's an upper bound on K star of N. I think typically that goes like into a half, or it's a number maybe just bigger than a half. So he has some sort of estimates there. But I guess they're quite heuristic. And so one of the things that I did in one of my earlier papers is I used this idea of this incomparability to also establish an upper bound on this K star of N. And I think that also, if I remember correctly, it also goes like into the 1/2. But if that actually, how tightly does that actually capture the K star of N, as opposed to just being an upper bound? I'm not sure we know.
It's actually interesting. That's like EMN type operators, right?
That's right. That's right. So in terms of actual hardcore data, I think, N equal to 81 was the largest that our little laptops were capable of. I mean, I guess we can extend it for another day or something and get N equal to 82. But at the moment, it's just sort of kind of using heuristics. Can we get upper bounds and that sort of thing? So yeah, but maybe the state preparation task might give some insight how to, think about that. Yeah.
Sorry, you said that K star R of S is a measure of the incomparability.
So K star of N is the minimum number of T operators that you need, whose normalized characters will distinguish R from S. But this other integer, that is what I'm claiming.
Swap.
Yeah, that's what I'm claiming measures the incomparability.
You said it's easy to read off.
That's right. It's somewhat easy to read off.
You can read off how incomparable they are.
Yeah, so I do have a small example. So if you take two partitions, so this one and this one, so this one would have 4 boxes in the first row, 2 boxes in the second row, 0 in the third row, 3 in the first, 2 in the second, 1 in the... So what majorization does is you look at the first entries and you say, okay, 4 is greater than 3. Then you add in the second entry. So what you're doing row sums. So 4 plus 2 is 6. And 3 plus 2 is 5. The inequality sign still faces the one direction, and then you must have equality. So actually, this guy majorizes this one because this inequality sign only ever points towards the one side. However, if they're incomparable, maybe these two, you start off with 4 and 3, it faces this way. Then 4 plus 1 is 5, 3 plus 3 is 6. Then the inequality sign swaps direction. So these two are incomparable. And what this measure does, it counts the number of times the inequality sign changes direction. And that, for some reason, it seems to be a good way of telling you if the normalized characters have a good, or are possible to be degenerate or not. So, yeah. So it's a very simple test.
We have a question online. I'll just send it through.
Okay, I will try my best. Okay. This is half BPS states in n equal to 4. Or do you want to read it here? That's better.
Oh,
I
my
don't
God.
speak the language.
So since half EPS states in n equal to 4 admit dual gravitational descriptions with rich geometric structure, I was wondering, does your algebraic formulation capture any aspects of this emergent geometry? And more broadly, do you see this approach as hinting toward a deeper unification between gauge theory and geometry? Very, very nice question. Yeah, so I mean, I think what I would say now, I guess maybe to be, I guess, fair, is I'm using this known correspondence that you've got all these nice states in the gravitational theory, the very heavy objects, the black hole-like objects, the giant gravitons, and through ADS-CFT, they're dual to some objects that live in the field theory. And in the field theory, then it sort of naturally suggests to us that we need to study these algebras, these symmetric group algebras, and yeah, finding nice properties and nice structure of these of the mathematics, and yeah, then just kind of using the duality to sort of infer results in the gravitational theory. And at the moment, it's, really, can we distinguish the one geometry from the other geometry, or, the one state from the other state? And yeah, so I would say yes, but only to a certain extent, I guess. And yeah, the other broader part of the question, I don't know. So, yeah.
Thanks. And we can probably discuss further
Yes.
this afternoon, but I guess for now, given the time, let's thank Gary again. Come back at 11.
There's another one here. Maybe this should go someplace.
Oh, okay.
Don't think I need to put it in front of Isabel.
Is that because I have a loud voice or nothing to say?
You've been trained well. Yes, you have a very. You're welcome.
All right, so let's start then the afternoon session. Well, actually, the second morning session. Oh yeah, before that, an announcement that the afternoon session, we were thinking of starting it a bit early, so 2 o'clock, just to give us a bit more time to move to the NITheCS for the public talks. Is that okay with everybody? So basically, lunch will be instead of until 2:30, it'll be until 2 o'clock, and then we meet here. Okay, we'll remind afterwards, just checking the time with everyone. Otherwise, yeah, let's start the second morning session with Will from UCP talking about quantum theory in small systems.
Amazing. Thank you very much. Thank you all for being here. I thought about changing the title also, but I stuck with it. But I wanted to give you a sort of a big picture context, which hopefully will touch on many people here and won't be just talking to Isabel as a potential collaboration partner. So the two big questions that I wanted to try to create a narrative around in terms of what I've been thinking about, what the group has been thinking about, and the places in which we might find useful places to collaborate are: how big does the system need to be for collective dynamics to emerge? And then how do I quantize a ball rolling down an incline? And the latter problem, you would think, man, how hard is a ball rolling down an incline? Even classically, that's not a very well understood problem. But coming back to the first problem, my first love, how big does the system need to be? Good. So normally we think from, say, a statistical mechanics class that we need Avogadro's number of stuff in order to think about collective dynamics. We think about the air in this room. We need 6 times 10 to the 23 particles. That's kind of the order of magnitude we need for collective dynamics to emerge. And then you have things like a beautiful phase diagram for water. Then going into high energy QCD, which is my area of research, one thinks about the phase diagram of nuclear matter. And one is probing this physics not with 6 times 10 to the 23 particles, but say 15,000 hadrons. Why 15,000? That's what we see in a central heavy ion collision at the LHC, order 15,000 particles. And we do ultimately see collective behavior emerge. I don't want to go through a whole lot of slides. I have very limited time because it's 15 plus 5. Good. And so in these sort of very large number of particles, we see some splitting, which I'm going to just tell you indicates that there's collectivity that's emerging, that there's a splitting between these two curves. And we can see this with numbers of particles down to 500 and even down to, say, 35 particles. And there are hints from low temperature physics that you actually need 6. You only need 6 particles for collective dynamics to emerge. So you'd think it was 6 times 10 to the 23. We're off by 23 orders of magnitude. It's actually 6 particles to get collective dynamics. And so what we'd like to do within the heavy ion high energy QCD context is to investigate collectivity or emergent dynamics in small systems. So I've spent my PhD working on energy loss in small systems. So we think about these high energy nuclear collisions. There's some kind of medium that's created. High momentum particles propagate through. They lose energy. How is that modified going from a large system where you're colliding nuclei to small systems where you're colliding, say, a proton on a nucleus or a proton on a proton? And how can we understand this experimentally? It's very important to me to make that contact with experimental measurement to do really phenomenology. Okay, super. And then there are fundamental questions from field theory in general. So we think that we're generating some kind of a thermal system, so we can do statistical mechanics in the quantum field theoretic sense. But what happens when you put quantum field theory in a small system and you have a temperature? And in particular, how do you say the equations of state change? How does the pressure, how does the entropy, how does the, what am I missing? Pressure, energy density, entropy, heat capacity, so on and so forth. How do those change because you're in a small system? And there's even just a question of how does one correctly formulate thermal field theory in small systems? And we'll come back to that in just a second. And similar question, so if we're going beyond leading order in these calculations, which is what you need to do in order to calculate equation of state and the trace anomaly, one needs to understand how to regularize a quantum field theory in a finite size box. So what happens when you remove all of the symmetries that you normally rely on when you use your regularization schemes? Okay, so I didn't want to spend a whole lot of time on the energy loss side because there's a natural collaborator to talk with about that. But there's all sorts of interesting calculations to do. And so if other people are interested or other students are interested in working on this, we can compute all sorts of interesting things and work on that together. But I want to spend a bit more time talking about thermal field theory. So this was posted literally today. Well, it came out on the archive literally today. So student Jens, the question was, compute rigorously the path integral formulation of the partition function in quantum field theory. And one gets the usual path integral e to the minus beta h. And the point is, sorry, let me take a step back. The point is that all the books do it in a very hand-wavy way. You introduce this decomposition of unity in terms of eigenstates of the field operator, and nowhere has that been well defined in a way that we can understand. We haven't even seen anybody attempt to really do it. And so he used coherent states, and shockingly, extra terms popped out. So you get the vacuum expectation value or the vacuum energy popping out, which doesn't happen in the usual textbooks. You look at Kapusta and Gale, you look at Das, so on and so forth. They don't get this term. And obviously that term should be there. Presumably it's not such a big deal that it's not there, but okay, one can think about things like Casimir effects because we're talking about small systems, and the vacuum energy is often referred to as the source of the Casimir effect. But there's this interesting coupling that's happening with the mass term. And so it seems like if you put a field theory in a box and you add a temperature, then you're getting some kind of system size dependent mass. And actually taking it further, going to the vacuum case and out scattering, it's possible, perhaps even likely, that this kind of a term emerges there too, and people just haven't seen it because they haven't been careful enough in how they derive their path integral.
I mean, really, when you renormalize with it, you renormalize the mass, does it matter?
In infinite volume, probably not.
Yeah.
Right? So you're going to set your counter term in the infinite volume limit. But now you ask, well, what if I put it in a small system? Well, that counter term was calculated in the infinite volume. And so now you're going to have finite size corrections from this piece here.
Right.
Yeah, so you're going to get a size dependence to your particle mass, which is very interesting. Okay.
Is there a plus sign there just before?
Yeah, exactly.
Okay, so.
So
You are also blocking part of the slide.
That's right.
Maybe you place the laptop here or?
When you say I'm blocking part, you mean this is?
I can read this part.
I can.
Now I can read, yes.
Okay, does somebody have a large Okay, I'll just try to.
I would suggest maybe place the laptop here and we can.
Oh, you mean when I'm like clicking? All right, fair
Yeah,
enough,
yeah,
fair
yeah.
enough, fair enough. All right,
So
good.
that way that will be covered.
All right.
Okay.
And I'll be a dancer.
You don't have to.
All right, good. Okay, so where can people collaborate? There's lots of low-hanging fruit. So we did this for 5-4 theory. So obviously one wants to go on to fermions to determine coherent states, field theory coherent states for fermions, gauge fields. As I mentioned, compute all these quantities at X linear order for say 5-4, Yukawa, QD, it goes on and on and on. One wants to compute Casimir effect, go on to heavy ions. And then what we're really interested in is trying to understand the finite system size corrections to the equation state for QCD. And it's not even clear what the sign is, the right sign of the corrections that are. Because if you look back in the 70s, all they say is, well, look, you get into a small system, so you have a small length scale, so you have a large momentum scale. Beta function for QCD is negative, so the coupling becomes weak. But if you open up your lattice QCD books, and they go through this in detail for a scalar theory, they get the opposite sign, at least in a 5-4 theory. So this is a very interesting question. I don't even know the sign, so that's a really interesting calculation to do. All right, and then maybe there's some lattice calculations where one can just directly calculate the trace anomaly in QCD on a lattice, or maybe start with super Yang-Mills if that's your jam. All right, good.
I'm sorry, is it okay to get the opposite sign in 5⁴ if the beta function is opposite?
So the beta function is positive, and they find that effectively the coupling becomes weaker as you put this in a smaller box. Yeah. Okay, good. So regularization. So all of our regularization schemes have disadvantages. So the common ones, momentum cutoff, polyvolars, zeta, analytic regularization, all these break gauge invariants. We like gauge invariants. Those are not going to be very good. The one that everyone uses is dim reg. However, there's a lot of issues with dim regs. You got to break Lorentz invariants if you want to get the axial anomaly. Gamma 5, Levi-Civita, these are hard to define because you're in some weirdo number of dimensions. It actually gets some finite integrals wrong, which I would want any kind of a regularization scheme to do correctly. Representation theory is unclear, right? Like, where are my fields living? Because we're actually in 4 dimensions, but are we really in 4 minus epsilon? And it's sort of weird that we are in 4 dimensions and we're trying to pretend like we're not. And for the purposes, the reason why I went down this route is that it's not amenable to finite size systems because you no longer have the rotational symmetry. So we want to do something different. And the idea is to regularize at the level of the Lagrangian so that everything is finite from the very, very beginning. So if I think about, say, 5-4 theory, I want to take my kinetic term to some analytic power. So that will obviously change the power of my propagator, and that will make everything finite. And this problem has been worked through with Jerry Bath, who's Costas's student, and he worked with me as a NITheCS intern. So he worked through the 5-4 theory, he worked through the Yukawa theory. Everything worked nicely to no one's real surprise, but it's a very nice calculation. And what we'd like to do is then go forward and extend to QED and really understand, I mean, the real goal that we would like to achieve is to see that BRST is maintained. We can maintain gauge invariance, confirm that that works at, say, next to linear order, and compute the axial anomaly, and hopefully everything comes out smelling like roses. It'd be very interesting to extend to SUSY. SUSY in dim reg is a problem because you have this delicate cancellation of the number of bosons and fermions depending on the number of space-time dimensions. So one would again like to confirm the symmetries and then extend to QCD. Okay, I'm already way behind. Maybe not, let's see. So quantizing rolling without slipping. So this is switching gears. The idea is I'd like to understand constraints in classical and then quantum mechanics. So if you haven't done constraints in a while, this is a bit of a reminder. So there are holonomic constraints and non-holonomic constraints. Holonomic constraints depend only on coordinates. So if you think about a mass on a string, then instead of x and y, I can use theta. If I have a bead on the rotating hoop, the classic problem. And then there's non-holonomic constraints, and these depend on velocities. And the canonical example is rolling without slipping. So there are many different examples, but the canonical one is rolling without slipping. For holonomic constraints, this is quite easy. You're able to use Hamilton's principle. You could, for example, reduce the number of degrees of freedom. As I said, go to theta instead of x and y.
Alternatively, you could introduce a Lagrange multiplier, vary the whole thing. And crucially, one has what's known as the transposition rule. So the variation of the velocities is equal to the velocity of the variations. And I don't know about you, I know when I learned classical mechanics, I saw this, one always uses this trick, and I was always disturbed by it, but I had no ability to hang a hat on anything about it. And it turns out that this is actually a very important and subtle issue that nobody talks about. So if we go to non-holonomic constraints, Hamilton's principle no longer works. You cannot reduce the degrees of freedom. You cannot introduce the Lagrange multiplier. Many people think you can. In fact, one of our referees at PRL thought you can, probably still thinks that you can. You get the wrong physics. It's called vaconomics mechanics. It's been known to be wrong for decades, but okay, whatever. And you lose the transposition rule. In fact, this is no longer the case. There are corrections. And it's interesting that this, Hamilton's principle is 180 years old. Classical mechanics is 400 years old. We're still learning how to do classical mechanics. So the general equations of motion for non-holonomic constraints were only found in 2011. And it was in this paper where corrections were derived for the transposition rule. So there's a lot of interesting things that people can work on in this area. So when I mentioned that Hamilton's principle no longer works, you can actually get it to work so long as you double your degrees of freedom. So if you do classical Schwinger-Keldysh and allow time to go forwards and backwards, computing, say, the expectation value of an operator in quantum mechanics and then taking the classical limit, if you then insert Lagrange multipliers that are, again, able to be doubled, varying this action allows you to derive the correct equations of motion. Now, this action just popped out of Alexander's head. He just said, oh, if I know what the correct equations of motion are, this is how I can construct an action that will give those equations of motion to me. He never derived it from first principles. So where can we go from here? Well, we have an action, so we can, in principle, compute a path integral for rolling without slipping. So it would be the first calculation from quantum mechanics of rolling without slipping. That would be an interesting thing to do. One would also like to derive this action from first principles, where I have really no good idea how to implement non-holonomic constraints systematically in the path integral. So how do you restrict the variations in your path integral for some non-holonomic constraint? Even for the holonomic constraints, it's a little bit dicey for me. And then would like to understand BRST and Dirac-Bergman in the classical mechanics and quantum mechanics setting. So working out in detail these canonical classical mechanics, quantum mechanics problems. So NITheCS intern Marcus Schmidt is thinking about these things right now, for example, and then would like to understand how to modify Dirac-Bergman for non-holonomic constraints. So implicit in Dirac's book, where he talks about his algorithm on page 2, he implicitly uses Hamilton's equations. He never tells you that, but he does. And so if you try to do Dirac-Bergman for a non-holonomic constraint, you're going to get the wrong answer because Hamilton's principle doesn't apply. You get extra terms. Those need to be computed. Last thing to talk about, gauges or constraints. So I've been talking about classical mechanics and quantum mechanics of point particles, but we are also interested in field theory. And field theories, the ones that we're most interested in are gauge field theories, and the specific gauge choice you make is a constraint. And I told you that non-holonomic constraints are non-trivial. Well, oh my gosh, the Coulomb and Lorentz gauges are non-holonomic because they depend on derivatives. So does the transposition rule hold for the Coulomb and Lorentz gauges, which we've used over and over and over again to derive our equations of motion? So everything works, so presumably it works, but we actually showed, yes, if you define integrable in some sense of like a total derivative, like a divergence, then you're able to do a divergence theorem. You're able to write your other coordinates in terms of the degrees of freedom themselves and not the derivatives. That's a crucial point, and that allows you to have the transposition rule working. But there's interesting things to go from here. So what student Ben is working on is thinking about non-integrable, non-holonomic gauge conditions. So you could have, for example, a combination of the Lorentz gauge and a real gauge, or you might have, for example, the 't Hooft-Veltman gauge. And the idea would be to show that you get the wrong physics by trying to implement those gauge conditions in the usual way, and then show how you could get the right propagator if you do the physics correctly. It'd also be interesting to consider non-abelian fields and to work through the consequences for BRST and BV. Okay, so that's what I wanted to talk about. Hopefully what I've convinced you, I didn't even call this conclusions, I call this outlook. So where can we work together to do interesting things? There's a lot of interesting things to work on. There's energy loss in QCD, thermal field theory in small systems, other people, interesting regularization methods in QFTs, if you're interested in QFTs, non-harmonic constraints in point particle mechanics and field theory, classical and quantum. Again, lots of interesting places to work on there. I didn't have time to mention, and it didn't really fit into the narrative, but I also have projects working on string theory and the classical physics of string theory, looking at numerical solutions of strings falling down in ADS space with student Nia. I think I've covered everybody. Tian also working on energy loss. And Jack also energy loss. Thank you very much. Thank you. Thank you.
Just one mention is that I think some string theorists look at N is equal to 4 superunions theory on small spheres. So they take small sphere and try to calculate that string exactly, kind of gets a result possibly similar to what you're getting. I'm not sure, but just, yeah.
Absolutely, yeah. So doing the gauge theories in small systems is technically tricky. So you would naturally go to a torus, and Ed Hooft showed in the 70s that you get these things called torons, where you have the gauge field wrapping around the topologically non-trivial structures. And so then you have to consider various vacua. And so I agree. I've seen various people do calculations on, say, SN instead of TN. So that's definitely a way to go and something to think about.
But you were looking at hard boundaries, right? Where the gauge field goes to 0.
I'm sorry, you're asking, am I looking at this?
Yeah, yeah.
That's
looking at a real box or a torus?
So far, we've worked in scalars and looked at both boxes and tori. And you see a stronger dependence on the box when you're Dirichlet boundary conditions versus periodic boundary conditions in a natural way. But yeah, there's some non-trivial things to think about going into gauge theories. One thing we might think about doing is somehow Higgsing the thing and having the Higgs field depend on space-time, but it's all up for grabs, what the right calculation is to do, or the one that would be the easiest to do, or yeah, right is some maximization procedure over a very highly dimensional, non-trivial space.
So you mentioned n equals 6. What 6 things are you counting?
Where did I mention n equals 6?
You're talking about the very beginning. You mentioned 6 particles were enough
Oh,
for collective behavior.
yeah.
What are you counting?
Number of particles. So this is I think it's just fermions and
Confined phase, you're counting number of confined particles?
yeah, like 6 particles.
There's a lot of virtual photons and virtual gluons in the game there, right?
No, this is a cold non-relativistic system.
I mean, something is holding the hadron together, right?
No. This is not. This is one of these sort of AMOE, trapped system things.
So what are the 6 particles you're counting?
I'd have to look it up. It's like rubidium or something like that. One of those things.
Nucleus, though, right?
It's an atom.
It's an atom. So there's a lot of position particles there. I wouldn't say you're counting 6. You're counting many already.
I mean, we always were interested in the number of relevant degrees of freedom. Exactly. Yeah.
That's the effective degrees of freedom are going to the atom. 6 effective. It's not you don't have the collective behavior of all the nucleons in the nucleus, right? That's not what you're.
Okay.
It's an effective.
Yeah.
But sorry, can I just add one thing? So
yeah,
they've done this they did this sort of ADCT calculation as well, didn't they? They calculated the shock waves, and they sort of were like, okay, you aim 3, but okay, maybe that's not so realistic. The ADCT isn't reality, so.
I don't.
This was a long time ago.
Yeah, I don't know let's chat.
Yes.
Well, I guess you kind of answered this question with your second to last slide, but I'll ask it anyway. So when you were talking about sort of quantizing rolling without slipping.
Yeah.
I mean, rolling without slipping is, to me, is a very macroscopic kind of thing. There's a whole lot of stuff going on.
Yeah.
It doesn't make, I mean, you might naively say, well, it doesn't really make sense to look at that in a quantum mechanical sense because this is something very macroscopic. But then in your second last slide, you talk there about sort of gauge symmetries are non-holonomic. So would you view this kind of calculation of quantizing rolling without slipping maybe some sort of toy model which is giving you a hand on gauge symmetries or something like that?
Yeah, it's a good question. Something I've also thought about, right? Because rolling without slipping is very specific. Like you're stuck on a point and you're just moving, and that actually doesn't quite feel quantum mechanical. That like, how does that square with uncertainty? And so, one interesting question when it comes to the non-holonomic particle mechanics, point particle mechanics is it even possible to quantize? And is there some like reason why it's not possible to quantize it? And I think that the answer is yes, you can quantize, and that there isn't some fundamental obstacle or obstruction. So that's one question. Then the second question, yes. So I see it. I mean, the gauge theories. It's not 100% clear to me the practicality of non-holonomic gauge conditions. Like, so it took quite a while to find any gauge condition that was not like very constructed for the purpose of coming up with a non-holonomic gauge condition. But the 't Hooft-Veltman gauge is non-holonomic, and you know it'd be very fun to show that 't Hooft was wrong on something.
Good luck with that.
Yeah, thank you.
Yeah, well, we already covered about fine, but if a quick question.
Probably wrong about quantum
I mean, we're not in a rush.
Yeah.
I'm not sure how quick of a question this is going to be, but I wanted to ask, what about in terms of explicit time dependence in the constraints, or passing to the QFT is explicit space-time dependence in the constraints? Does that affect anything about this procedure or the context we're in?
Generally, no. So when you implement the constraints, often it's referred to in the literature as you look at the variations in frozen time, like you freeze time. So what's important is that the variations in your path at any particular time are consistent with the constraints. And that's what it means by the time is frozen. So you're thinking about your path, and at any particular time, varying that path for that particular time. So introducing time dependence to the constraint doesn't appear to cause any kind of an issue. There is, in the same way that holonomic is some weirdo Greek word that somebody in the 20th century or 19th century came up with, there is a terminology for constraints that are time dependent versus not time dependent. So not time dependent is scleronomic and time dependent is rheonomic. But I feel like that there's nothing important in that distinguishing those.
Yeah, well,
Yeah, you're welcome.
All right, let's think.
Super. Thank you very much.
Okay, good. So I'm going to be talking about some work done with Vishnu and another collaborator of ours, Suresh Nampuri. So just to outline the talk, I'm going to be talking, I think, probably reviewing some stuff that other people have talked about, maybe with black hole thermodynamics, black holes and string theory, and supergravity. I'll talk about the attractor mechanism for black holes, which shouldn't be confused with the attractors in chaos, I'll talk about our work, which is hot attractors. And then I'll talk about two sort of work in progress, which is trying to understand these hot attractors from a Euclidean perspective. And I definitely am not going to get to the last part, but I'll just mention it because that's also a work in progress. And it's trying to look at this issue using some very fancy GR, which is called the covariant phase space formalism with introducing boundaries. For those, anybody who's done GR, you learn all this fantastic covariant stuff and all this wonderful formalism. And then you look at the Hamiltonian formulation of GR and it's just horrible. You like throw away all your covariants and all the nice tricks you learned and just have a very non-covariant way of doing Hamiltonian mechanics in GR. But the covariant phase space formalism is a way of actually looking at Hamiltonians in GR and generalizations of GR in a covariant way. Which does, but I don't think you can deal with non-holonomic constraints in that formalism, but I'm not sure. I haven't thought about it. Okay, so quickly, black hole thermodynamics. So black hole thermodynamics, we looks at some properties of black holes and identifies, going way back, and a lot of people talked about this, so identifying certain properties of black holes with normal things in thermodynamics. So for example, the zeroth law, which says the temperature is constant throughout a body in thermal equilibrium in terms of black holes, maps to the event horizon surface gravity as constant. And that's because we identify the surface gravity of a black hole with temperature. We've got the first law of thermodynamics, which is basically the conservation of energy. And black holes satisfy a particular differential equation like this. And it's hypothesized that this can be identified with the first law. The temperature of the black hole turns out to be associated with the surface gravity. And famously, the entropy, at least for simple black holes, is associated with the area. And you can also have change of the angular momentum and changing charge. And the second law, entropy always increases. For black holes, we've got the entropy of the black hole and the entropy of the universe, and that always increases. But here, the change in entropy of the black hole is the change in the area of the event horizon. Okay, so the attractor mechanism is a feature of extremal black holes in supergravity or supergravity-like theories. And for this class of black holes, the moduli, or which are basically scalar fields that you have in the game, are always drawn to fixed values at the horizon, no matter what they started off with, asymptotically far away from the black hole. And these values at the horizon only depend on the charges carried by the black hole, which is related to its entropy, and as I mentioned, independent of the starting point. Okay. Because the entropy of the black hole is related to the area of the horizon, and these scalar fields take on various fixed values at the horizon, they don't depend on what's happening at infinity. Okay, so initially it was thought that this depended on supersymmetry, but it's known now that that doesn't require supersymmetry. Okay. Let's just go to sleep. Right. Don't worry about the details. I just wanted to just briefly to give you some context. So we're looking, in the simplest case, we're looking at a theory with gravity, some scalar fields, and some U1 gauge fields. And the coupling for the gauge fields depends on the scalars. You can vary that action and you get equations of motion for gravity, for the scalar fields, and for the gauge fields. And in the simplest case, we look at some sort of spherical symmetric ansatz. You can look at, say, just magnetic charges to be simple, but you can introduce electric charges as well. And because we're assuming spherical symmetry, we just assume that our scalar field has radial dependence. And it turns out that there's an effective potential which governs the behavior of the scalars, which just depends on the charges that we put into the ansatz. Okay, so the end result of looking at the solutions is, as I mentioned, we find the attractor mechanism, and this attractor mechanism is governed by this effective potential. And if you find the minimum of that effective potential, that turns out to be the values that the scalars take on at the horizon of the black hole. And the area of the event horizon is related to the value of this effective potential at the minimum. So the entropy of the black hole is related to the minimum of this effective potential. Okay. So I'll talk this. I just want to record them for later. These are the two equations that came out looking at this attractor mechanism. I've put in that b squared for later. Basically, the effective potential is minimized, and the value of the effective potential can be related to the area of the event horizon, which is related to the entropy. Okay, so this is my work with Vishnu and Suresh is on, you saw what happens when you take these black holes which obey the attractor mechanism, which only happens at 0 temperature, and you heat them up a little bit. So that's why we call these hot attractors. So we consider the black holes which obey the attractor mechanism in the limit that you take the temperature to 0. And when you give it a non-zero temperature, they've got two horizons that we can say at R plus and R minus. R plus is the outer event horizon, and R minus is the second inner event horizon. The simpler examples would be like the Reither-Nordstrom charged black hole or the Kerr black hole. And normally the entropy of the black hole is associated with the area of the outer horizon. Okay, so it turns out that these hot attractors have some interesting properties. So you have, you've got two horizons. So you've got an area of the outer horizon and the area of the inner horizon. And people noticed quite a long time ago that if you take the product of these horizons, so when you have the 0 temperature black hole, in the attractor mechanism, the area of the horizon only depended on the charges carried by the black hole. Okay. Now, when you heat them up, that doesn't happen. That doesn't happen anymore. The area of the outer horizon can depend on the values of your scalar fields at infinity. But if you look at the product of the area of the inner horizon and the area of the outer horizon, you find this geometric mean law that no matter the area of the outer horizon and the inner horizon, no matter what the temperature is always equal to the square of what the area you had for the extremal black hole. So this has been observed for a large class of black holes. And nobody had any real explanation as to why this happened. This also generalizes to all entropy, except there seems to be some caveats and exceptions to that, which I don't really understand. So our old work was to prove that this geometric formula holds, and we showed how it just follows from the equations of motion. I think we're still struggling to find a convincing deeper reason for that. Maybe Vishnu understands, but I don't think we have a convincing deeper reason for that. But just to say that we generalize this to higher dimensions, we got more complicated formulae, which I won't distress you with, for gauge supergravity. And that's interesting in that you can have more horizons, and then you get formulae that you have to combine the area of multiple horizons to get some invariant, which you can relate to the area of the extremal horizon. And interestingly, these extra horizons can be imaginary horizons. Yeah, okay. So these can be roots roots of your metric, which you only get if you take your coordinates to be imaginary, but they still somehow contribute to a generalized entropy law. Okay. So we have for when you have these two horizon black holes, you have a first law, which is just the outer horizon, and you can get something similar for the inner horizon. And if you want these equations to have the the same form, you need to take the temperature of the inner horizon to be negative. We can chat about that maybe in discussion time. But it's still not completely clear to me what this negative temperature means and how we should interpret the entropy of the inner horizon. Okay, so I'll just go. So just carrying on a few more details about the hot attractors. So we have the same equations of motion when you have hot attractors. The scalars take on values at the horizon that depends on the values at infinity, so it's not attractive. So here in this plot, we have the horizon, and the values that the scalars take on the horizon are independent of those at infinity. But as I talked to before, we can still construct robust invariance in this case. Okay. And what we found is, so these were the attractor equations at 0 temperature. And from what we found was we found that if you average these quantities between the inner and outer horizon for the hot black holes, you had the same equations being applied. But now, instead of just being applied at the horizon, you had to average them between the horizons. Okay. Since I'm running low on time, let me try to get to at least some new stuff. One of the things I'm thinking about is trying to get a Euclidean perspective on the hot attractors. So Wick rotation is a nice trick in flat space. So you send time to imaginary time, and this is just like going to the complex plane to evaluate some real integral that would be difficult otherwise. And in quantum field theory and on the lattice, it's totally essential to help with the convergence of path integrals. So we go from some path integral we can't evaluate to some Euclidean path integral we can evaluate. And as long as sometimes we're careful, sometimes we're not careful, but if you do that in the right way and don't cross any singularities, you should get the same answer. Okay. So it also, as Will talked about, I guess, it relates time and temperature. So if I write the inverse temperature as beta, this Wick rotation, you start off with a partition function, and if you Wick rotate, that gives you a trace of your evolution operator. So U is the evolution operator, and it takes you from time 0 to time t. But because the trace is starts and ends at the same state, in order for this trace to make sense, we have to put periodic boundary conditions on the time. So when you want to relate time and temperature, you have to put periodic boundary conditions on time, and then you can do this trick. Okay. Okay. So this is tricky in curved space because, well, a lot of reasons. So which is the time coordinate that you should rotate? And you can rotate the time coordinate one part of your space-time, and then if you do the same rotation in another part of the space-time, you get a complex matrix, which can be difficult to interpret. So just the key message is that Wick rotation is tricky in curved space-time. But you can always do a Wick rotation locally. And in particular, you can do it at the horizons. So when you do this at the horizon of black holes and you apply smoothness, the time periodicity gives you the temperature. Okay, but doing this in general can be tricky. Okay, so this is what one often does with a black hole. So I look at the Euclidean black hole, and what was the null surface in the Lorentzian signature just becomes a point. And if I want this point of the cigar to be smooth, I need my time coordinate to have a particular periodicity, which gives you the temperature of that black hole. Okay, so smoothness and time periodicity give temperature. So you can also do that between the horizons. And when you do that between the horizons, you can do that at the outer horizon or the inner horizon of one of these black holes. So it's always easy to do Wick rotation at a point. So I can do this Wick rotation near that horizon. I can do that Wick rotation near that horizon, and you get something which corresponds to the temperature of the inner or the outer horizon. But the problem is it's difficult to work out how to do this whole, to do this recruitation for the whole space-time between the horizons. So one thing I was thinking about and a little stuck at the moment is trying to, if I want to relate this Euclidean path integral to these attractor equations, I would need to have the Euclidean geometry, the whole Euclidean geometry between the horizons. And that's something I'm kind of stuck at the moment. And as I said, I'm not going to get to the covariance phase-space formalism. So that's where I'll end the talk and we'll take time for questions. Thank you. Yeah.
Could you please go to the slide where you have written the action for the attractor?
Yeah, okay, so that's just gravity with scalars in a gauge field.
So, but generally, if you have scalar field and it's back reacting, then the Cauchy horizon vanishes. Why it's not happening here?
Okay, there you go. So yeah.
Generally, if you have a scalar field which is back reacting, then the inner horizon vanishes.
Okay, so the idea is that whether or not so we find if we just look without the back reaction, we definitely find interesting relationships. So I'm not saying that the inner horizon is necessarily something physical or it's not unstable towards Cauchy perturbations, but this kind of classical inner horizon is somehow an echo of something interesting that can happen. So it might make sense when you, in the same way that, let's say from, some people would say the horizon isn't real. Okay, it's something you get when you average, it's some classical thing that comes out as an average over some geometries. So in the same way, there's maybe, there isn't really an inner horizon, but it is telling us, it seems to be telling us something about the entropy and the physics of the black hole. So yeah, so I don't really know the answer to that question, but it's hoping that we can uncover something about the entropy of the black hole, even if it's not necessarily, strictly speaking, a sensible classical object.
No, but when you were writing this equation.
Yeah, which equation?
The equation of motion, there is no. These are probe scalar field?
No, there's no probe. I'm just looking at the solution. So I'm not looking at perturbations. Well, I mean, if you look at the zero temperature black hole and look at perturbations, there's no problem at zero temperature. Obviously, at finite temperature, it's a whole different story that people have studied before. But at zero temperature, there's no problem with perturbations. Yeah. So yeah. Yeah. Yeah.
I'm not sure if I quite caught it. Those attractor equations you do over lowercase b, and you said you would get to the lowercase b.
Oh no! So I've just written so b. This b. That's the area of the horizon.
Okay.
So I mean, so this doesn't make sense at the zero temperature. The numerator is zero.
Yes.
So I can always divide by whatever I like. But so that's the zero temperature equation. But when you get to the finite temperature attractor equations, this is the quantity you have to average between the horizons to get zero.
1 minute or two for questions. Could you say in 1 or 2 minutes what the covariant phase-space problem is?
Basically, it's like so normally you've got this nice covariant formulation of Hamiltonian mechanics using symplectic forms. So this basically, so the covariant phase-space formalism is a way of rewriting the Hamiltonian mechanics of GR and generalizations of that in terms of forms. That gives you a sort of a covariant way of writing, rewriting the Hamiltonian formulation.
Because you're doubling your dimension because now you're working in phase space.
Yeah, so it's you're working in phase space and you've got variations which are described by a particular form. And so you've got all this nice, you're working with one forms, and well, you've got things which are one forms in phase space, but not necessarily one forms in real space. So anyway, there's a whole lot of games, and it's quite a fun formalism to play around with.
Useful for what? Like what can be
Okay, so
applied to?
in particular, this all comes down to kind of understanding the first law. So you can derive the first law using the Hamiltonian formulation. Normally people do it in a non-covariant way. You can do it using the covariant formalism. And yeah, I was hoping that answering some of the questions about what's happening with this hard-to-track mechanism could be nicely done using this formalism. So in particular, you can look at space-times where you have boundaries, and then it becomes interesting that's precisely what we're worried about, is what's happening to our fields at the boundaries, at the inner and outer horizon, and what are the boundary conditions you apply, and you just have to kind of evaluate some form on a boundary that's easy to do if it's exact, et cetera, et cetera. Yeah. Okay.
Good. All right, then let's thank gentlemen. And we break for lunch, and as we said, we'll be back at 2 o'clock for the discussions.